Okay, in this video, we are going to discuss the order topology on a given set. Uh, in order to define order topology on a given set, we are going to use simple order relation on that set. So let me first recall simple order relation on the given set. Okay. Simple order relation, simple order relation, or just the order relation. Okay, so since the Munkar books use simple order relation, that's why I'm saying simple order relation. But instead of simple order relation, you can just say order relation. Okay, now, so what is the order relation on the given set? Let's define the order relation on the given set. Let's say X is a given set. So here is the formal definition. Let me give you the definition and then I'll give you some example. A simple order relation, a simple order relation denoted by this symbol, on the set X is a relation satisfying the following three properties. So I will discuss what are those three properties. So before that, let me make it clear that this symbol, we are just using it to denote the simple order relation on the set X. We are not specifying this symbol is strictly less than symbol in the set of real numbers. So we all are very familiar with strictly less than symbol on the set of real number, but we are not specifying that this symbol is strictly less than symbol that we often use in the set of real number. In fact, strictly less than on the set of real number is an example of the simple order relation. We will see it later, but this symbol, so this symbol, we are using it just to denote the simple order relation on the given set as X. We are not specifying this one is the strictly less than symbol. Okay, now let's X is a given set, a simple order relation denoted by this symbol on the set X is a relation that satisfies the following three properties. And the first property is called the comparability. It's a comparability. So let me write down this property first and then I'll explain it for every X and Y in X. For every pair of element in X for which X not equal to Y, that means if this X and Y, they are two different elements, then either X is related with Y or Y is related with X. So basically this property, it tells us that if you have any two elements in the given set X, and let's say these two elements are not the same element, or we can say like that. Let's say if you have any two different element in the given set X, then these two elements should be comparable under this relation, under this relation. And if those two different elements, they are comparable under this relation, then that is called the comparabilities of the element of X under this relation. So this property, it tells you that in order to be this relation is a simple order relation. If you have any two different element in the given set, those two elements should be comparable under the given under this relation. That's the first property. Second property is non-reflexive. Non-reflexivity. So let me first write down this property, and then I will explain it. For no X in X, so this one is an element in the set X. For no X in X, does the relation X is related with itself hold. So basically this so here this property is non-reflexivity. Now let me tell you what is the reflexivity. If you have a relation on the given set X, then that relation is called reflexive if every element of the given set is related with itself under that relation. Then the relation is called reflexive. But here we are saying the non-reflexivity. That means every element of given set X, it should not be related with itself under the given relation. In order to be the relation is a simple order relation. That's the second property. First property is comparability, second one is non-reflexivity, and the third one is transitive. Okay, transitivity, which is also called transitivity. So let me tell you, let me state this property first. If X is related with Y and Y is related with Z, then X is related with Z. So this property, it tells you that if you have three elements in the given set X, let's say the first element is X, second is Y, and the third one is Z. If X is related with Y and Y is related with Z, then X should be related with Z. So this property is called the transitivity. I'm sure you all have seen this property somewhere in lower level math classes. So if the given relation satisfy all three properties, comparability, non-reflexivity, and transitivity on the given set X, then that relation is called simple order relation. Okay, let me give you couple of example. So here I'm gonna give you two example. One of them is an example of simple order relation, and the other one is a relation which is not simple, or which is not simple order relation. First one, let's say X. In our definition, we are assuming the set is X. That's why I'm just writing X is R, where R is the set of real number. Then the relation, which is now strictly less than, okay, strictly less. Then now this strictly less than relation is a simple order relation, the simple order relation on X, or on the set of real number. It is easy to take this strictly less than satisfy, or strictly less than relation satisfy those three properties of simple order relation. First property, comparability. So that means if you pick any two real numbers, different real numbers, then one of them is always strictly less than the other one. That's the first property. Second property, non-reflexivity. that is quite obvious, because if you have a real number, you cannot say that real number is strictly less than itself. And the third property, transitivity, is quite obvious. So this strictly less than is a simple order relation on the set of real number. Okay. The next one is, let's say x. We have a set x with more than one element, or let's say more than one element, or we have a set x with at least two elements. And let's say this one, I'm sure you guys are familiar with this notation. This one is called the power set on x. So basically this is the power set of x. Power set of x means is the collection of all the subset of this set x. Then the relation let's take the relation which is subset. Usually we denote the subset like this. So then the relation subset is not a simple order relation. Is not a simple order relation on the power set of x. This is because the subset does not satisfy the first property of simple order relation. First property, which is the comparability, is not mandatory that two subset of the power set, or the two subset of x, or the two elements of the power set are two subsets of the given set, or the two elements of the power sets, they may not be comparable. Okay, it's not mandatory that two subset of the given set are comparable. That means one is the subset of other, or the other one is subset of the first one. That is not mandatory. That's why the subset this subset is not a simple order relation on the given set, on the power set of the given set. Okay, so these are the two examples. First one is the example of simple order relation, and the second one is a relation which is not the simple order relation. Now we are ready to define the order topology. Now let's define the order topology, and then I will give you a couple of examples. Let's say X is a set with a simple order relation. So we have a set with the simple order relation. Let's say X is a set with the simple order relation and has more than one element. So let's say X is a set with the simple order relation. So we are taking X with the simple order relation because we going to when we are dealing with topology, there is always the basis of that topology. And now here we are going to use the interval, open interval, half open interval, to define the basis for the order topology. That's why we need the simple order relation, and it has to have at least two elements, because simple order relation is related with the comparability. So if there are two elements, at least two elements, then you can compare one of them with the other one. That's why we need at least two elements. Okay, let's say X is a set with the simple order relation and has more than one element. Now let script B be the collection. Script B be the collection of all sets of the following three types. Okay, so now let's say script B be the collection of all the subset of X of the following three types. The first one is all open intervals, all open intervals a b in X. So this guy script B is the collection of the subset of X, and those subset, there are three different type of subset, and one of them open intervals. Okay, and the second one, the all intervals of the form A0B. So here in the first one, both are, we are using parentheses, that means they are open, like the open interval in the set of real number. And here they are also called the half open. So the left side is included, right side is not included, where this guy A0 is the least element of X if the least element exists. If the least element exists. Okay, if the set X has the least element, then this collection has also this type of the open interval, and half open interval, and obviously there are the open intervals of the first type, and if the set X has the least element, then in addition of those open interval, this collection also has this half open interval, such that the left endpoint of this half open interval is that least element. And the third one is all intervals of the form A B0. It is still half open interval, but the right side is included, where B0 is the greatest element of X if the greatest element of X exists. Okay, it's not mandatory. If you have a set, it's not mandatory that it has to have least element or greatest element. Some set could have both. Some set just can have just least element but not the greatest, and some set they may not have like both of them. For example, set of real number, they don't have both. They don't set of real number doesn't have like the least element and also doesn't have like greatest element, but the set of positive integer, it has least element but not the greatest element. Set of negative integer, it doesn't have the least element but it has the greatest element. Okay, all right, so X is the set of simple order relation. X is a set with a simple order relation and has more than one element. Now we are taking script B as a collection of the subset of X of these following three types. If X has if X doesn't have least and greatest element, then this script B is gonna be simply the set of first type. If let's say if X has the least element, then the script B is gonna be the collection of first and second type, and let's say X has both least and greatest element, then script B is gonna be the set of first, second and third types. It depends on your set. Okay, now here the collection, this collection, the collection script B is a basis, is basis for a topology, is basis for a topology on X. Okay, now it is easy to check that this collection script B, it forms a basis for a topology on X. Then that topology is called the topology is called the collection script B is a basis for a topology on X, and that topology is called the order topology on X, and which is called order topology on X. Okay, basically the topology generated by this collection, the collection script B, the topology generated by this collection script B is called the order topology on X, and these are the elements of these basis script B. Now let me give you a couple of examples of the order topology in the given set X. Okay. Now, first example, let's say X is the set of real number. Just let me remind you the standard topology on R. So we have discussed the standard topology on R in our previous video. So standard topology on R is a topology generated by the basis, this basis. Okay, script B whose elements are simply the open set on R, or open intervals in R. Is the topology generated by this basis. Okay, so where A is less than B and A and B are the real numbers. So we have seen this or we have discussed the standard topology on set of real number in one of our previous video. Okay, let's say X is a set of real number with the simple order relation strictly less than. Okay, all right, now here so if you look at the definition of simple order topology, you need the set with the simple order relation. So our simple order relation is strictly less than, and then also the set, it has to have at least two elements or more than one elements, and obviously R has more than one element. Okay, now let's see. Now let's see what is that collection. If you go back to the definition of order topology is the topology generated by this this basis or the collection script B of those three types. Now in our example, let's see what is going to be this collection. As I said earlier, the set of real number doesn't have the least element and also doesn't have the greatest element. So in this collection, or in the basis of order topology on R, on the set of real number, is going to have only the element of first type, because there is no least element. If there is no least element, you cannot have the second type of element in script B, and also if there is no greatest element, then you cannot have the third type of element in the script B. So that means in our example, this script B or this collection is going to be simply the collection of all the open intervals in R. Okay, so the script B, which is the basis in our definition, is gonna be simply the collection of first type of element, and in first type of element they are simply the open intervals A, B, such that A and B are the real number and A is strictly less than B. Okay, now you can see here the basis is the set of open intervals, and we know that the topology generated by this basis, which is the standard topology. You can see here, so standard topology is the topology generated by this basis, and the basis of the standard topology and the basis in the definition of our order topology, they are exactly same thing. So we can say that order topology on the set R with the strictly less than simple order relation is the standard topology. Okay, so the order topology on R, and if you take the simple order relation is strictly less than, then the order topology on R is the standard topology. Okay, the standard topology. So that's the one example of order topology. Now let me give you one more example, and the second example is, let's say x is the set of positive integer, that means which are like 1 2 3 4 and then keep going. Okay, now you can see here this set and still the we are taking simple order relation is strictly less than. Alright, now here you can see that this set has the smallest element, which is 1. Okay, this set has the smallest element, which is 1, but it doesn't have the greatest element. So that means in our collection or in our basis in the definition of order topology is going to have only two type of these sets. Let me go back to the definition. Obviously the first type of the set, since the set of positive integer has least element, so in the basis also we're going to have the second type of element and the first type of element, not the third one, because it doesn't have greatest element. Okay, now it could be that basis and one so if you remember the definition of the basis is basis is basically the collection of the subset of given set, such that each element of your set, it has to be in one of the it has to be in at least one of the element of script B. So that means here, so these are the elements of our set. So each integer they have to be in this they have to be in one of the set in this collection, or one of the interval in this collection. Since one is the open interval, sorry, one is the least element, so as I said before, our collection is going to have the first and second type of element. Since one is the least element, so this one we can we can see here one is going to be in this interval. So this is one is the least element of this set. So this is second type of element, and then in order to be this collection basis, you have to have at least each element of this set has to be in at least one element of script B, and this one is going to be in this interval. Okay, and then also we need the interval here in this collection, such that 2 is going to be in at least one of them. Similarly, 3 is going to be at least one of them, and 4 is going to be in at least one of them. Now we know that we know that this collection is going to have the first and second type of element, and since one is the least element, so this is our second type. Now we can include 2 in this interval, right? 1 2 3. This is the open interval, that's the first type. 2 is here, and then 3 we can include 3 is in this open interval, 2 and 4. If you take this to open interval in this set of positive integer, this obviously 2 is going to be here, and then if you take the open interval, this open interval in the set of positive integer, 3 is going to be here, and then so on. Now here you can see that, so that this is going to be our collection. So next one is going to be 3 5 and then so on. That will contain 4. So now this collection is the basis in the definition of our order topology. Now you can see here each set or each interval in this collection is a 1 point set of the set of positive integer, because this one the half open interval, or this half open interval, it contains only 1, nothing else, because we are just taking the set of integer. Now you can see here 1 and 2 is not included, so this has only 1, and this one is open interval of 1 3, so only the 2. 1 is not here, 3 is also not here, so only going to be 2. And then here 2 is not included because this is open interval, 4 is not included, so only the 3. And then the next one is gonna be 4, and then so on. Now you can see from here our basis is consisting with 1 point subset of the set of positive integer. So these are like, this is the 1 point, or these are the collection of the singleton, or you can say this is the collection of the 1 point subset of the set of integer. And we have seen before, if your basis it's consisting with 1 point, it's consisting with all 1 point subset of the given set X, then that basis generates the discrete topology on the given set. Since our basis discrete B it's consisting with all 1 point subset of the set of positive integer, so the topology generated by this basis is going to be discrete topology on this set of positive integer. So which means our order topology on this set is a discrete topology. Okay, so the order topology on G plus, which is the set of positive integer, is the discrete topology on G plus. Discrete topology is basically, this is the collection of all the subset of G plus, or is like a power set. Okay, all right, that's all for order topology.